In this, our last lecture of the semester, I'll cover fundamentals of transistor-level logic. You probably remember from CSCE 211 that digital signals are conveyed as discrete voltage levels, where a zero binary value is typically associated with ground voltage or 0 volts, and 1 is associated with the power supply voltage, usually referred to as VDD. In the early logic families of the 1970s, VDD started out at 5 volts, but advancements in semiconductor technology have allowed it to be steadily and continuously reduced, all the way down to less than 1 volt today. And why? Why is it? Why do we want to reduce the supply voltage? Because power consumption scales at VDD squared, but more on that later. In reality, there is a range of voltages that represent each logic level, which allows digital logic circuits to be resilient to noise sources. So basically, 0 values can be greater than 0 volts, and 1 values can be less than VDD. Noise sources include wire resistance, which causes the voltage to drop the further it passes along a wire. Power supply noise, in which the supply voltage changes due to the logic gate switching activity causing temporary spikes on the supply voltage, and crosstalk or capacitive coupling between neighboring wires. This leads us to the static discipline, which states that every circuit element must produce valid outputs when given valid inputs. Just as with the dynamic discipline that we covered in a previous lecture, the basic idea is that you're given certain technology parameters along with a set of rules that your design must not break. For a given semiconductor technology, VIL, or voltage in low, defines the maximum input voltage allowed to represent a 0 input value. This way, any voltage from 0 to VIL is considered a logic 0 input value. VOL, or voltage out low, defines the maximum output voltage permitted for a 0 output value. This way, any output voltage from 0 to VOL is considered a logic 0 output. Similarly, VIH and VOH, which stand for voltage in high and voltage out high, define the minimum voltage allowed for a 1 input and 1 output value. So any voltage between VIH and VDD and VOH and VDD is considered a logic 1 for the gate input and gate output respectively. Voltages that fall between VIL and VIH are considered to be in the forbidden zone. Forbidden because using these voltages with logic gates will produce unpredictable results. The VIL, VIH, VOL, and VOH values are determined by the behavior of the gate's input response. So in other words, for a given semiconductor technology, you build a logic gate and then you look at its input response, and from that you can determine what these 4 values are. Consider a simple buffer gate, which works like an inverter but doesn't invert the input. So an input of 0 produces an output of 0, and an input of 1 produces an output of 1. What could possibly be the function of such a gate? A signal booster. But let's examine this gate relative to its input responds. In other words, what happens to its output voltage as we increase its input voltage? As you increase the input voltage starting from 0 volts, you will see that the output voltage will rise very slowly until a point where the output will raise quickly and then level off and then slowly converge to VDD. The point at which the output voltage begins to increase sharply is the point where the slope of the output transitions from less than 1 to greater than 1. Specifically, it's when the slope equals 1. Right? So when the slope of the output voltage hits 1, this is called the unity gain point. Another unity gain point occurs when the output voltage levels off. In other words, when its slope transitions from a value greater than 1 to a value less than 1. The x-axis location of the first unity gain point is VIL, and its y-axis location is VOL. So the x-axis here represents the input voltage, and the y-axis represents the output voltage. So if you look at the two unity gain points, the x-axis location of the first unity gain point is the VIL, the input low, and then the corresponding y-axis location is VOL, voltage output low. And then when you go to the second unity gain point, the x-axis location of that is VIH, and the y-axis location is VOH. Generally, VIL is higher, much higher than VOL, and VIH is much lower than VOH. The difference between VOL and VIL is the lower noise margin, or NML, noise margin low. While the difference between VOH and VIH is the upper noise margin, or NMH, or noise margin high. So in other words, if you look at the output of a gate, its output tends to be cleaner than what its input signal needs to be. So its output is going to be closer to the ground and VDD levels than what is needed for it to interpret the input. So the noise margins define the amount of noise or signal degradation that can occur between a gate's output and another gate's input that you're driving. Now let's switch topics to logic gates. Logic gates are made out of transistors, and transistors are made out of a semiconductor material, usually silicon, for CMOS logic gates, which is basically the logic technology that modern processors are based on. Silicon is in column 4 of the periodic table, meaning that it is a group 4 element, and that also means that it has 4 valence electrons, 4 electrons in its outer electron shell. Pure silicon can form a crystal structure in which each atom forms covalent bonds with 4 neighboring atoms, each about a half nanometer apart, and each bond is at a specific angle, which forms a unit cell, a cubical unit cell, a cube-shaped unit cell, which is about 5.5 nanometers per side and consisting of 18 atoms. And when I say unit cell, a unit cell is the smallest unit of repetition. So a unit cell has 18 atoms inside of it, which form a lattice structure, and then that structure repeats in 3 dimensions throughout the crystal structure. Silicon crystal is a poor conductor. It has a resistance of 21 million ohms per centimeter, which is a really bad conductor. Which, if you compare that to copper, copper has a resistance of 1/1,000,000th of an ohm per centimeter. So silicon is about 21 trillion times less conductive than copper. But silicon can be made more conductive by adding foreign materials called dopants into the crystal structure that allow for charge carriers to move about in the crystal. Weakly doped silicon crystals contain 1 impurity per billion silicon atoms, whereas highly doped semiconductors contain 1 foreign atom per 1,000 silicon atoms. So in other words, you have a choice of how many foreign atoms you want to inject into the crystal, and when you inject these foreign atoms, the foreign atoms take the place of silicon atoms in the crystal. So if you dope a crystal, silicon crystal, with a group 5 element like phosphorus, phosphorus atoms replace some of the silicon atoms in the lattice, but this adds an additional electron which is mobile. So it's free to move about the lattice, and that electron can carry current through the lattice. So in other words, the dopant atom is fixed in position, but its extra electron can move. These electrons are considered majority charge carriers. So keep that in mind. Majority charge carriers. Silicon that is doped this way, in other words, with a group 5 element, is called an N-type silicon, where the N stands for negative, since the majority charge carriers have negative polarity. Likewise, you can add a group 3 element like boron, which replaces some of the silicon atoms and allows for a hole or a lack of an electron to be mobile and free to move about the lattice and carry current. The holes are, in this case, the holes would be considered the majority charge carriers. And silicon that is doped this way is called P-type silicon, where the P stands for positive, since the majority charge carriers have positive polarity. A Mosfet, or a metal oxide field effect transistor, when viewed from the side, kind of like cross-section, as shown here, is a multi-layer structure consisting of, and if we start from the bottom and work our way up, so the bottom is the substrate, which can, for example, be a P-type silicon, and then you've got these 2 little islands of N-type silicon embedded in the substrate, which are called the source and drain. And then the gap of substrate material between the source and drain is called the channel. And above the channel is a layer of insulating glass made from silicon dioxide. So you might be wondering, like, if you go to the beach, you see beach sand, is that silicon? That's actually silicon dioxide that you see on the beach. That's not pure silicon crystal. Silicon dioxide is obviously silicon with oxygen, and it is actually a very good insulator. It conducts very, very little. And so silicon dioxide, or sometimes just called glass, is used as insulating layers on a chip. And then above that insulating layer is a layer of highly doped polycrystalline silicon called polysilicon, and that's called the gate. Now, in the past, instead of the poly, there was a layer of metal there, which explains the anachronistic naming of Mosfet. So metal oxide semiconductor, that's actually naming the materials from top to bottom as compared to bottom up, which is what I just did. So you used to have metal oxide semiconductor, the semiconductor being the channel, whereas modern MOSFETs use polysilicon then the oxide, and then the semiconductor. But they still call these MOSFETs. So you might notice that the gate, oxide, and channel form a capacitor because the oxide is an insulator. And if you put a positive charge on the gate, this will create a positive capacitive charge that attracts the minority charge carriers in the channel. The minority carriers are the opposite type of the majority carriers. So in the p-doped silicon or p-type silicon of the channel, the minority charge carriers are electrons. And this accumulation of minority charge carriers in the channel effectively joins the source and drain with charge carriers of the same type that are in the source and drain, or the majority charge carriers of the source and drain. So you end up with source and drain both with electrons as the majority charge carriers, and then the channel connecting them that has minority charge carriers, which are electrons accumulated in there. And this ends up allowing current to flow between the drain and the source. Without this, there's no current. Current doesn't flow because current can't flow from N to P-type. In other words, you can't go from the N-type of the source and drain into the P-type silicon because of the diode effect. And you can't go from the channel into either the source or drain because the channel is grounded. So this is called an N-type transistor, or an NMOS transistor, or an NFET. So N-type transistor, NMOS transistor, or NFET, all the same thing. And this is because it uses N-type charge carriers in the channel. In other words, the N-type transistor connects the source and drain, electrically connects the source and drain, when the gate is 1, essentially, or is VDD, and 0 otherwise, or technically I should say anything above VIH would connect the source and drain, because the gate is going to be connected to the inputs of the logic gate. So as I mentioned before, in order for there to be a capacitor formed between the gate and the channel, the substrate of course, which is also the channel is part of the substrate, must be grounded, which it is in an N-type transistor, but when you turn on the transistor, the channel voltage at either side will begin to appear to have the same voltage as the source and drain. So, as I mentioned, the channel and the substrate are grounded, but when you turn the transistor on and current starts to flow between the source and the drain, the channel voltage begins to look like the source and drain voltage, as opposed to the substrate voltage. So ideally, you want each side of an N-type transistor, when it's on, to be connected to voltages close to ground. Because otherwise, the higher voltage of the source and or drain will close the gap, the voltage gap, with the gate. In other words, the gate voltage is relative to the channel because of the capacitor effect. You've got, the gate and the channel are two sides of a capacitor. The voltage of the gate is, with regard to the capacitive behavior, is relative to the channel. And so the channel grounded fine, but when the transistor's on, you also want the source and drain to be close to ground as well. Otherwise, the higher voltage of the source and drain will pinch off the capacitive effect. You'll have the voltage of the channel will effectively raise up and close off the voltage potential with the gate. And this will cause loss of charge carriers in the channel. So what does this all mean? Well, basically what it means is that an NFET is supposed to have its source and or drain should be connected to ground, right? So the NMOS is the part of the logic gate that will be connecting the output of the logic gate to ground. This is also called the pull-down network. It pulls the output of the gate down to ground. That's the job of the NFET. You don't want to use the NFET to pull up to VDD, because if you do that, your source and or drain will be at a higher voltage, which will work, still works, but it doesn't work well because you don't get a large enough voltage difference between the gate and the channel, right? A P-type transistor, on the other hand, or PMOS or PFET, has the opposite types of silicon for the source, drain, and substrate. But unlike the N-type, where the substrate or the channel, when the transistor is off, is connected to ground, in the P-type transistor, the substrate is connected to VDD. This way, a ground value on the gate, if you ground the gate, if you connect gate to 0, actually looks like negative VDD relative to the substrate, which attracts minority carriers in the channel, which in this case would be holes. So you have the minority charge carriers in the channel, which are bridging the gap between the source and the drain, which have majority charge carriers, holes. So in other words, the P-type transistor connects the source and drain when the gate input is 0. Now in reality, the gate voltage is going to be negative VDD, but for the purpose of designing with PFETs, you just think of it as a 0. You put a 0 on the gate, and that will turn the P-type transistor on. So a 1 on the gate turns an NFET on, and a 0 on the gate turns a PFET on. And as with the N-type transistor, you want the source and drain to be close in voltage to the substrate voltage to allow for maximum minority carrier concentration in the channel. So you want the gate to be as far as possible away in voltage from the channel or the substrate, which of course is normally connected to VDD. So the source and our drain should be close to the VDD levels, which is why the PFET is used to pull up the output of the logic gate. So the result of all this is that the P-type transistors are used to pull up a logic gate's output to VDD, and the N-type transistors are used to pull the gate's output to ground. So for every input on a logic gate, you need to have a PFET and an NFET that's responsible for either setting the output of the gate to 0 or to 1. So a little bit more specifically here, the P-type transistors will have one of their sides, and it's actually, the source and drain are sort of interchangeable, but the convention is that with the P-type transistor, it's the drain is connected directly or indirectly to the VDD. It might be connected indirectly through another transistor series, through another transistor. But the drain is where the drain side is the VDD side. And the source side, which is the other terminal, is connected directly or indirectly to the logic gate's output. And again, when I say indirectly, I mean it may be connected through another transistor in series. And then the N-type transistor will have its source connected directly or indirectly to the ground, and the drain directly or indirectly connected to the logic output. The logic gate's inputs are connected to the transistor's gates. So every logic gate must have one N-type and one P-type for each input. So to summarize this, each logic gate has a pull-up network consisting of P-type transistors and a pull-down network consisting of N-type transistors. But there's one important consequence of this. If the P-type transistors are responsible for setting the output to 1, and the P-type transistors only turn on when their gate input is 0, that means that no logic gate can ever output a 1 unless at least one of its inputs is 0, right? So you have to have at least one input 0 in order to turn on at least one of the transistors in the pull-up network, which are all P-types. So if you look at the truth table for any gate implemented in CMOS logic, any of the rows of the truth table that have a 1 output have to have at least 1 0 input. That's going to cause an issue for the AND gate and the OR gate, for that matter, which both have a 1 output when all their inputs are 1. Well, that makes, if all their inputs are 1, you can't have a 1 output because there would be no way for any of the PMOS transistors to be turned on. Likewise, if the N-type transistors are pulling the output to 0, and the N-type transistors only turn on when the gate input is 1, then no logic gate can ever output a 0 unless at least one of the inputs is 1 in order to turn on at least one of the N-FETs, N-type transistors. So again, that's an issue for AND and OR gates because both of those types of gates output as 0 when all the inputs are 0. Okay, so if you're not entirely clear about this yet, let me show you some examples. So we'll begin with an inverter. This is a simple one. So it has one input, it has one P-type transistor, one N-type transistor. The input pin of the inverter, which is called A, connects to both transistors' gates. The PFET has one side connected to VDD and the other side connected to the output pin, which is Y, while the NMOS, the NFET, has one side connected to ground and the other side connected to the output Y. Now, you might see a potential problem here. If both transistors are turned on, then the output will simultaneously be connected to VDD and ground because the NMOS and the PMOS transistors will both be turned on, and that's probably not good. However, because the NMOS and the PMOS transistors turn on under opposite conditions, and since both gates are connected to the Y output, each of the two transistors are turning on under mutually exclusive conditions. So when the input is 1, the NMOS transistor connects the output to ground, and the PMOS disconnects the output from VDD. And when the input is 0, the NMOS disconnects the output from ground, and the PMOS connects the output to VDD, which creates the inverter effect. Now, a 2-input gate will have 2 PFETs and 2 NFETs, but the PFETs are connected in parallel while the NFETs are connected in series. If you look at the truth table here, each row having an output of 0 corresponds to a path through the pull-down NFETs, and each row that has an output 1 corresponds to a path through the pull-up PFETs. So for each of these, you only need to consider the 1 inputs when designing the pull-down transistors, and only the 0 inputs when you're designing the pull-up transistors. So if we look at a row with a 0 output, you'll see that both A and B are 1. Since the 1 value activates the NFETs, you can connect them in series, meaning that both transistors need to be on to pull the output down to 0. Now, once you've designed the pull-down transistors, it's actually really easy to design the corresponding pull-up, because it's the opposite in the sense that instead of series, the PFETs are in parallel. On the other hand, you can start with the rows of the truth table having a 1 output. Since there are 3 rows with 1 outputs, we would want to create a parallel path through PFETs for each one of these 3 rows, of course only caring about the inputs in those rows that are 0. The first row has a 0 input value for A and B. This means that you would have a PFET for each of these inputs connected in series. If we go to the next row with a 1 output, A is 0, B is 1, so we ignore B. So A, we have a PFET for A connected from the output to VDD. And then finally in the third row with an output of 1, B is 0, so we would have a PFET for B connected to VDD and to the output. So now we have 3 parallel paths. The problem, though, with this is that the parallel path in which you have A and B, PFETs for A and B in series, is redundant, because that path isn't necessary, because if both A and B were 0, it would simply activate the 2 paths that we already have to VDD and pull the output up. So you can actually, you don't need the path with the A and B NFETs connected in series, so we can eliminate that. The other thing to keep in mind here too is that in CMOS transistors, you only need to have each input needs to be only connected to one PFET and 1 NFET. So if we had left in the 2 NFETs connected in series, we would have ended up with an imbalanced gate. So in this case, starting with the pull-up network was more complex, since there were more rows with a 1 output than there were rows with a 0 output. That's why I generally start with whatever output value has the least number of rows, and then build the other side as a complement, converting parallel paths to serial paths, or series paths rather, and vice versa. For example, a 3-input NOR gate only has 1 output row with a 1 output, which is when all the 3 inputs are 0. This way we could connect 3 PFETs in series and connect the 3 NFETs in parallel. Since there's no way to build an AND or an OR gate in CMOS, as I mentioned earlier, to achieve the same behavior, you would need to use a NAND or an OR gate with an inverter connected to its output. I previously covered tri-state gates in Lecture 3. Tri-state gates are a way that an input and output can be connected or disconnected depending on another input called the control input. Tri-state gates are built using transmission gates, which is a PFET and an NFET connected in parallel with the control input, which controls whether the input and output are electrically connected or not, is connected to the gate of the NMOS, and a complemented form is connected to the gate of the PMOS. This arrangement is necessary because NFETs, as I mentioned earlier, pass strong zeros and PFETs pass strong ones, so we need to have 1 gate for each possible input value to the transmission gate. You might have learned in CSCE 212 that the power consumption of digital circuits is comprised of a dynamic portion and a static portion. The dynamic portion comes from when a digital circuit changes between pulling its output down to pulling its output up, at which time the gate is having to charge the capacitance of the wires and other gates connected to its output. The energy required to charge a capacitor of capacitance C to a voltage of VDD is C times VDD squared. And discharging a capacitor is free. So when the switching rate is F hertz and half the transitions are pull-ups, we can estimate the dynamic power consumption as 1/2 times C times VDD squared times F. The static power consumption is due to the leakage current that passes through the pull-up and pull-down networks at all times, even when the gate's not switching. And this is because transistors that are in the off state still have finite resistance. That's typically on the order of mega ohms, or possibly tens or hundreds of mega ohms, but it's non-zero. The static power consumption is this leakage current, which is also called the quiescent power supply current, which is IVDD, and when multiplied by VDD gives you the static power consumption. The last topic we'll cover is memory arrays. At this point in the class, you're comfortable with the behavior of RAM arrays, having used them in your register file and the instruction memory. But I haven't yet covered how RAM arrays are designed. The three most common RAM technologies are dynamic RAM or DRAM, static RAM or SRAM, and flash RAM, which can be of the NAND or NOR variety. I'm not going to cover flash in this lecture. I'm going to focus on DRAM and SRAM. All RAMs, though, including flash, are generally arranged physically as a two-dimensional array of cells where each cell contains one bit. We'll assume for this discussion that the RAM has one memory port. So there is, inside of this two-dimensional array of cells, there is one word line for every row of cells, and there are a set of bit lines that connect each cell in each of the columns. At most, one word line can be asserted at one time. When a row's word line is asserted, all of the cells in that row are connected to their bit lines. The bit lines serve as both the input and the output to the row. By default, the bit lines will be driven to the bit values in the row, but if you drive the bit lines with a strong enough signal, the bits in the row will be changed to the new value. The difference between DRAM and SRAM is the internal design of the cells. In DRAM, the cells are a single capacitor and a single NFET transistor, which connects the capacitor to the bit line when the word line is asserted. In SRAM, the cells are designed as cross-coupled inverters that kind of face each other, with two NFETs that connect each side of the bit line when the word line is asserted. Because an SRAM cell requires 6 transistors, and a DRAM cell contains only 1 transistor, DRAM is cheaper and denser than SRAM. However, this difference doesn't necessarily cause there to be a difference in access time between DRAM and SRAM. The access time is affected more by the size of the decoder that converts the memory address to the word lines. Larger memory arrays require a larger decoder because there's more word lines, and the latency of the decoder scales with its size. This is why larger memories in general are slower in access time as compared to smaller memories, since DRAMs are usually larger than SRAMs because they have a higher density, and so in effect that causes DRAMs to be slower than SRAMs. So that's all we have for this lecture. I hope you enjoyed the class, and if you are taking the course for a graduate or honors credit, or if you want to do an extra assignment for extra credit, please watch the next video in which I describe Lab 4. Thank you, and have a great winter break.